I'm going to take you back to the galaxy, and I'll try to go quickly because we're all very eager to hear the next talk about why there's a universe. So Planck, as you've seen in earlier talks, detects a lot of emissions from the galaxy, so that in principle allows us to get at interstellar medium science. I'm going to tell you perhaps a few insights, maybe some new directions. It'll be a bit of a random walk, and if it seems erratic at times, you can, I think these days, call that non-Gaussianity. So here's my perspective. The universe has some baryons in it, but a lot of them are wasted. They don't even end up in galaxies. And there's some galaxies which don't even have an interstellar medium. They've got rid of it completely. Those would be good galaxies from which to study the CMB. But alas, our galaxy has an ISM. It also has this interesting phenomenon near the galactic center. There is a theory for it. It's called a monster. The monster in our galaxy is a bit of a pussycat. If it had been a big monster, it might have cleared out the interstellar medium and we'd be an elliptical galaxy, but we're not. So we're in a spiral. There's still an interstellar medium, and Jim Peebles will like this because you can see the stars forming and all the beautiful structure. These things seen edge on remind us that they're a disk, and we live in one, and it's the dust in that dusty disk which is one of the problems, one of the foregrounds to the CMB. An overarching question in ISM science is, why is there still an interstellar medium in a galaxy like ours in which stars are continually forming? Why hasn't it been used up, for example? So I like to call this how the Milky Way ticks. And I Googled and found this beautiful watchworks. And you can see from this that the galaxy is much more complicated than cosmology. Because in cosmology there's 6 parameters, we're told. That would be 6 gears. But this one's got a lot more epicycles, doesn't it? I'm interested myself in finding how things tick. And that you could, the analogy in the clock would be, well, what gear drives what gear, and how does it come around to affect the whole mechanism? So I hope to be able to point out a few of those connections in my talk. We have to be grateful for being in a spiral, because I think ab initio we'd never figure out how stars form and planetary systems and so on unless we were guided by some data. And if we weren't doing this, how could we be having any fun at all? An ISM research program, broadly writ, could be described in the magenta words, a bit about galactic ecology, how things fit together. Certainly we have to understand about feedback from star formation, recycling from star death, and probably infall from intergalactic material still arriving at our galaxy. And the whole thing's very complex, just like that clockworks that I showed you. Now, we're humans, and we like to look at details, don't we? So astronomers are like that, and we can peer into the finest mechanisms in the clock. And I think this is one of the things that Planck is actually going to offer us. It's going to enable regional analyses. We're going to be able to use Planck data to understand things on small scales, different than analyzing the whole sky. And I will assert that Planck will impact ISM science just because of this. Now we have downloadable products. Think of what IRAS has done over the years. Think of what Planck will do over the next decades as people mine this data set. Let me tell you a bit about star formation, since that's part of why there's an ISM and why it will wind down in the future. Planck sees the reservoir through the dust. So I'm going to be an astronomer, and I'm going to mine the reservoir, and I'm going to pull out my favorite star-forming region, recently W3, giant molecular cloud, and see what it looks like. So there's what it looks like from the Planck Legacy Archive. You can see that there's quite a bit of opacity because that's what we can measure with this product, and there are some bright spots and so on. And if we hadn't been spoiled by Herschel and Spitzer in having very good angular resolution, if we were back in the days of IRAS, this would be a pretty stunning thing to have. But we have Herschel. And that kind of ruins the whole picture, you would say. But they're related. I lined them up. So. But if you're studying star formation, the name of the game really has been the companion satellite, Herschel. And there have been lots of studies, and they're summarized here. Key projects: Gould Belt Survey, Hobbies, from which this was a project, and Huygens, wrapping right around the galactic plane, but only plus or minus 1 degree. So one thing Planck can do is look, of course, over all of the sky and things that we have not targeted with Herschel. Another thing that Planck can claim is it's the broad shoulders on which Herschel is standing, because every one of the maps that Herschel makes, if you're interested in things that like column density and so on, the tau from a Herschel map at that fine scale, you have to add in the 0 point. And we've been doing that since 2010. I've given you the reference to Jean-Philippe's paper, and there's an interesting poster that you can have a look at. So Planck is buried in to the Herschel product. Planck also did an all-sky survey looking for cold clumps. This is the blind survey, and it's described in the papers that I mentioned there. It's been followed up by Herschel to see what's inside of the Planck cold clumps, and that's very interesting. And there will be further follow-ups with, or there have been with Bolocam, with WISE, etc. Session 12, we'll hear a bit about these sources as well as some extragalactic ones. So let's pause and, or not pause, but we should rush on and talk about where did this high density structure come from. You should read this 58-page review, and then you'll probably understand a lot more about this than what I can tell you in a few seconds. But it looks turbulent. We can measure the 1D power spectrum of an image and learn something about the scale of the structure. There's no preferred scales. It just looks like a power law. And I would say that we can still look forward to better and better numerical simulations that help us understand why that power law structure has come to be. So let's look at the power law structure. What can Planck tell us? Well, if you look in the likelihood paper, you will find a clever way of fishing out what the power spectrum of all sky dust probably looks like. And it has a power law spectral index of minus 2.6. And that number you've heard before. Not minus 3.00, but it's a bit flatter than that. So, connecting the gears in the clock, what would it look like if you actually looked at something that traces most of the material, the gas, rather than the dust? We can do that because we have lots of H1 data, and the Parkes and the Bond surveys are going to give us a lot more. So this is just a bit from the GBT. It's just a 12-degree field. You can see there's lots of structure there. This structure is spread out in a velocity cube, and we can see different parcels of gas. We call them local and intermediate velocity and high velocity gas. And the first two have strong dust-gas correlations. They're the strong mixture of the dust in with that gas. So if you measured the power spectrum of those components, you would think, well, maybe we should get minus 2.6 or something like that. So we did that. Here is the north ecliptic pole field. And you can see the model of power law of a certain index. You can see the effect of the beam at high K rolling things over. And you can even see that we understand the noise in this data. So that's for this field, and we did lots of fields, and here are the results. They scatter around, they bump around between -2 and -3 between fields, but fairly close to what Planck tells us all sky. I think that some of those changes are actually real from place to place. And it's actually an interesting thing to study, but we can't pause for that at the moment. But as you see in the title for this slide, there's a tremendous range of scales over which similar power spectrum indices are found. Even the high velocity clouds come in with indices like this. So to form that structure, to understand the formation, I think there's two major transitions to think about. One's from the warm neutral medium through a thermal instability into the cold neutral medium. This idea has been around since actually before I was a graduate student, and that was the last millennium. But that theory never told you how much of each phase you ought to have. So it's actually very interesting to do the numerical simulations to discover more quantitative things like that, and I give you a recent reference to that. The second transition is from the atomic phase into the molecular phase, which is traced by CO. So that gives me a segue into talking a bit about CO. At the bottom, I mentioned the magnetic field, but Francois has talked about, and I'll come back to that at the very end. So Planck has given us a nice all-sky CO product, and I remind you that that's what astronomers call WCO. It's the integral over the line profile over all velocities. We don't have the velocity resolution with Planck. And out of the plane, interestingly enough, there's a lot of CO outside of where the nuggets of molecular clouds that you might have known about from ground-based studies. And that allows us to look at this transition region and the nature of what we've heard about the dark gas. There are papers on this, and Gombe is going to give us a talk in session 7. I'm going to mine the archive in a few slides to show you an interesting result from that product. So the dark gas, this looks a bit like a tabloid, but you can go through this quickly. The phenomenon basically is that sometimes there's extra emission or optical depth that you can't trace with one of the standard gas tracers. And in white, you see the standard explanations. Maybe there's some H2 gas that doesn't have any CO yet. Maybe it's in that transition stage. Maybe there's self-absorption in the H1, so you've underestimated the H1. In both of those cases, you would actually then conclude that there's more dust than you had accounted for because there's missing gas. An alternative is right at the bottom on the slide. What if the dust that's mixed in with the gas just emits more? It has a higher opacity. So here's the ugly slide on what opacity is. It's basically just tau over NH, or it's how many centimeters squared cross-section for emission do you get in your partial of gas. So it's immeasurable because we can measure tau and we can measure NH. And what we found in the early papers is that even in the diffuse interstellar atomic medium, the opacity isn't one number. It's not a constant. The dotted crosshairs there intersect a sigma of 1. And that was a nice round IAU type of proved number that you could remember. But you see there's factors of 2 a change relative to that. And you notice that they go along that locus. Black locus drawn between over the data. That's a locus of constant emission per unit particle parcel of gas. And if you remember that emission is just what was absorbed and these grains are in thermal equilibrium, that's a constant you could think of interstellar radiation field striking this material, assuming common absorptive properties. So that's pretty interesting. There's nothing special about the temperature. The temperature is just responding to changes in the real dust opacity. So inspired by this, we had a look at some Herschel data, and we could, again, calculate tau from Herschel maps with 0 points from Planck. And we could get an estimator of NH, and we could plot them up. And you see that this is log-log, and the constant slope is not what goes through the data. So this is a nonlinear increase of opacity with column density. And since this is a cloud, a nearby molecular cloud, probably column density corresponds to volume density. So there's some evidence of the physics that might be going on. We explored a bit with BLAST in the early days to see what we could find out about the opacity. And notice how the scale has changed now. All of the Planck data that I showed you has been pushed over to the left. You also see the green vertical line. That's the number for the opacity that's adopted in our key projects in Herschel. So the Herschel people believe that dust has evolved in the denser regions where they're going to be measuring masses of cores and filaments and so on, and that's the number that has been obtained from some theoretical calculations 20 years ago. So I showed you this. Where does this data plot on this diagram? It plots about there. You can see it coming in. So again, there's evidence that opacity is changing from place to place, and I would think that that's another thing to ponder when we're wondering about dark gas. It also has an impact on anything related to mass, because if you get the opacity wrong, you don't know what the mass is. And this is factors of 2, maybe 3 uncertainties. So dark gas, this opacity, how much dust really is there? So I'm going to take you on a path here where there's another way of measuring how much dust there is, and that's through scattered light. And this is an old idea that I learned about when I was a young faculty member. This paper by Sandage is a brilliant paper. He really nailed the issue and figured out everything that was going on. So the only thing that's changed is that now with modern technology, you can do this almost from your backyard. Well, it has to be a dark backyard. So I'll show you some of these new horizons that I'm quite excited about. What can you get if you start doing this optical imaging of reflected light off this dust? Well, you get better resolution than most instruments, for example, even with a small telescope. You get a consistency check on the strength of the interstellar radiation field that's powering the dust emission. And you get to measure the amount of dust and whether it's evolved, including dust in putative dark gas regions. So let me just give you an example of the Draco Nebula. There's a nice poster out there by Lens. You should go and look at that. It's a very interesting region. But one of the reasons that I selected it for a trial photo for scattered light was because, in fact, it had already been detected by WIT. And prior to that, well, you can actually see it on the Palomar's plates if you're a wizard like Marc Antoine and can pull it out. So let me tell you a bit more about this region, then I'll show you the scattered light. So that's not a Planck image again, it's Herschel. Really interesting region. Looks like along the lower left, a working surface as this cloud is blasting into the upper part of the halo. And I'm going to show you, I'll blow that up So that's still the Herschel image. And here's the reflected light image. All those white things are, for you cosmologists, those are called stars. And they're a mess, but fortunately there's space between the stars. And I just go back and forth. I didn't align these electronically or anything. I'm just an amateur, but it's actually staggering. It almost makes you believe that this thermal emission that we're seeing from Herschel and Planck is actually dust, because surely this scattered light is from dust. So here's an interesting piece of archive that I did. I just went and pulled out the tau map, and I lined it up. That's the green. And I went and mined the CO map, and sure enough, where it's lots of scattered light, lots of Herschel emission, lots of tau, that means Planck emission, that's where you see the CO. But there's big streamers coming out away from the working surface, and that's where we want to look at quantitatively how much scattered light that we have to measure how much dust there is. And how do you do this? Well, you buy a fairly expensive Canon lens that has super coating, and you put it on a mount and you send it to New Mexico. And the wizards doing this are Bob Abraham and Peter Van Dokkum. And now we have a system of 10 of these all on one mount, and it just rips along. So I've got a few minutes left, Torsten?
Sweet.
Okay, yeah, I can do it. So AME you're going to hear a lot about, and you should. It's a very interesting component that Planck is really nailing. What I would like to say about it is read these papers, go to the talks, but more the thoughts that are written here. If it's spinning dust, it's related to the very small particle component of interstellar dust or large molecules. And some part of that fraction of small particles causes the so-called unidentified infrared bands, which are often called the PAH features, or it's carbonaceous of some sort. Some people like to call this amorphous carbon nanoparticles these days, because if you say nano, you can get more money, I'm sure. But the thing to think about is the connection, because what's powering the UIR emission in the mid-infrared had to be absorbed somewhere, and it's absorbed in the ultraviolet interstellar extinction, and it's part of the extinction curve. And we know that there are changes of extinction curve with environment. The small particles disappear at the edges of molecular clouds. We can't probe right through clouds because the star suffers too much extinction. So listen to Clive's talk and think in the future. I think as we move across the whole sky, we can explore things like this, whether we can see AME signatures of dust components appearing and disappearing in different environments. And we should surely look at the polarization of this. The ultraviolet dust that causes the extinction, well, the extinction in the ultraviolet, it doesn't polarize. So there might be some relationship here. Anyway, go to those talks. Why are they interested in small particles anyway? Well, they're apparently very important in our theories, anyway, for heating the atomic gas and for molecule formation because they're large surface areas. Finally, Francois told you of the great impact that polarization is going to have. And I've pointed out again the papers that you should read and the posters that you should go to. Just look at the middle magenta point, I think is really going to be interesting. Planck will show us some of this, how the magnetic field orients relative to structures. We want to know what is the influence of the magnetic field on the formation of structure in adding pressure that resists collapse of gas, etc. Planck won't tell us everything. In the future, though, I think there are some interesting experiments. There will be ground-based experiments too, some of which I haven't mentioned here, but there are a couple of stratospheric balloons that are going to fly which will have better resolution and will, at least in the nearby star-forming regions, help answer this question about the role of the magnetic field. And that brings me to my end. I thank personally this Canadian Space Agency, but I thank you all in the Planck collaboration, because it's a great human collaboration and the data are just fantastic.
Thank you. Thank you. Questions, please. We have ample time for questions. Okay, I have one. Usually the dust spectrum is modeled with a beta parameter, which varies across the sky. How sure can we that this is a correct description of the dust emission?
Well, if you're talking about beta that Marc-Antoine talked about, I believe, in the modified black body, I think if it had been 2.00, we could be very confident we understood it, because that would tell us that there was crystalline material in space and we'd be done. But it's not. It's not quite as steep as that, and that is telling us something, probably about the amorphous nature, which we've got clues about from other points of view. In detail, of course, there's possibly many different types of grains, and they have different sizes, and each size has a different temperature in exactly the same radiation field. So it's really complicated in detail, and maybe we should just at this time be thankful that we have a way to parameterize it. But I think, as Marc-Antoine has shown, the taus that are coming out, at least at the intermediate to high latitudes, are probably pretty reliable now. There's probably not a huge mixing of grain temperatures along the line of sight like there would be in the galactic plane. So if you avoid the galactic plane, we probably have a pretty good idea now on betas, taus, and the temperature that goes into that.
More questions? Yep.
You were speaking about dark gas. Can you just recall the conclusions you have?
There are dark gas is probably an unfortunate name, like dark matter and dark energy, but we all have our dark side. It just means that there are some regions of the sky where naively using other markers of how much material there is, CO and H1 measurements, and assuming that dust and gas are well mixed, there seems to be too much emission. So it could be that we're missing some gas and therefore missing some dust, or the detour that I went on is that possibly we're not missing a lot of gas. It's just that the dust has a higher opacity in those regions. I wouldn't push that as the overall explanation, but I'm very confident that one value of the opacity for dust is we've moved beyond that.
Okay, one last question. Yeah.
He works just down the hall from me, but he had to come over here to ask the question.
So regarding the observation of scattering light by dust grains, so we all know that dust grains are aligned with magnetic fields. So if we observe the scattering light by aligned dust grains, so we should observe the circular polarization. So can you comment on that?
You're going to live longer than me, so maybe you'll be able to measure that. Certainly true, people have looked at it in the solar systems at Iacolight, for example. I thought about it when I was much younger. We haven't even measured the linear polarization of that scattered light yet, and that would be interesting because it's like clouds over the city with all of the street lights shining up instead of down. There will be some polarization there.
Okay, thank you again. Our next speaker and the keynote speaker of the day is Andre Linde. He will talk about fundamental physics and the formation of the universe.